Hello, everyone. I hope everyone's doing well tonight. Welcome to another virtual planetarium show from the UCLA Planetarium. My name's Aidan Gibbs. I'm a graduate student in the Department of Physics and Astronomy at UCLA. And usually the graduate students do all of the planetarium shows, but today we actually have a special show where we're going to be talking about the James Webb Space Telescope. And so I'm not the only one doing the planetarium show tonight. I'm joined by our special guest, Dr. Tiffany Kataria, who will be talking more about the James Webb Space Telescope. But for those who don't know, the James Webb Space Telescope is a new telescope that's going to be launched in a little under 2 months. It's scheduled for December 18th. And this is going to be the biggest space telescope that's ever been launched. In many ways, it's going to be sort of a successor to the Hubble Space Telescope. And it's going to be certainly one of the most important observatories in astronomy for probably the next decade or even longer. So we're really excited about it. It's sort of been 20 years in the making, thousands of people working on this telescope. So it's quite exciting. So Tiffany is going to be telling you about that during the first part of the show. The second part of the show, as usual, is going to be a night sky show where I talk about the sky in Los Angeles tonight and show you some things you can see in the night sky. So you can expect that later. And also, we'll let you know that we're going to be doing another show for the James Webb Space Telescope launch in December, on December 1st. And that is planned to be in person at the moment, depending on the current sort of COVID conditions. So you can look forward to that as well. But without further ado, I'll introduce our guest speaker. So Dr. Tiffany Kataria is a research scientist at NASA's Jet Propulsion Laboratory, and she received her Bachelor of Science in Physics and Astronomy at Stony Brook University, and then she did her PhD at the University of Arizona. And her current research centers on the study of exoplanet atmospheres using three-dimensional models. So Tiffany, go ahead and take it away.
All right, thanks Aidan for the introduction. Let me go ahead and get started here. Oh goodness. Share. Oh goodness, we should have checked this earlier because of course, no wait, hold on. I think this is working. I had a minor panic. All right. Lesson learned, do a test. Okay. All right. Well, thanks again, Aidan, for that introduction. So yeah, as described, I'll be talking a bit about James Webb, but really, some science that I find particularly exciting. So towards the end of the talk, I'll be highlighting some of the programs that I'm involved in that I'm really excited about, getting new science, getting new observations from. And this is just to start off. I'll be including lots of pretty pictures of James Webb because it's gonna. I wish we could, take see it up close when it launches and unfurls, but this is what it's gonna look like up in space. All right. So anytime I kick off a exoplanet talk, especially to a broader audience, I like to kind of put everything in context, and so I start with Earth. Think of Earth and think of all of the complex processes, the properties of the planet that are there. The numbers of water clouds, the land, the oceans, the life, the vegetation that's present on the planet. And so take all of that stuff that you can think about when it comes to Earth, good and bad, and collapse all of that into a tiny, tiny dot. And so this is actually the image of Earth, the pale blue dot image, very famous, taken by Voyager 1. Carl Sagan, wrote about this pale blue dot. And so, viewed from afar, all of that complexity, all of that all of those properties, all of those processes are all, this is kind of, even a better case scenario of what exoplaneteers have to face when it comes to observing exoplanets, because this is actually within your own solar system. And in our case, we're studying exoplanets, which are planets in other solar systems. So we're actually, viewing these from even further distances. And so, getting at the properties of these planets, what they're made of, how they formed, what we can learn about these things is ever more challenging, because we're essentially thinking about these tiny dots in space. So we have to be clever about how we use our telescopes to learn as much as we can about exoplanets, about these exotic worlds that we see in other systems. And so, just to provide some context, as I've said, exoplanets are planets beyond the solar system. So these are planets that are potentially orbiting other stars and other systems. And so really at this point, I'd say that exoplanet science has entered this era of a lot of understanding of, characterization. And when I say characterization, it's not just finding these planets, which is the first part, but also understanding all the properties, how it formed and evolved, and which is a lot of what I'll be talking about today. But again, just to provide some context, here on the right, I've got a histogram that shows the number of exoplanet detections per year. And so the first exoplanet detections were made in the mid-90s and continue apace today. The different colors on the histogram bars show the different detection types. And so the first two here I'm showing both in animations are really the first two that were, and the current ones really, that are discovering quite a few planets. So this first technique called the radial velocity technique, essentially, so both of these are actually indirect techniques. So you're actually staring at a star, looking at its properties, and inferring that a planet is there. And so in the case of radial velocity, you're measuring the Doppler shift of the star. And so they would, one thing you might think of when you think of Doppler shift or the Doppler effect is when you hear an ambulance siren go by you. And so when it's coming towards you, it's very high pitched. And then when it recedes, when it leaves, where you're standing, it could perhaps sound lower in pitch. And so that's essentially the Doppler effect in motion. And so that's essentially what the radial velocity technique is trying to accomplish, measuring those shifts. And so the shift is actually accomplished because of the planet that's there. It's actually gravitationally tugging on the parent star. And that's actually a measurable thing that we can measure with telescopes. So radial velocity has found quite a few measurements. And with that measurement, you can actually measure the planet's mass. And so something that's more massive is going to cause a bigger tug than something that's less massive. So a complement to that technique is the transit technique, and you might have heard a lot about it via different missions, which I'll talk about a little bit. But transits, again, are an indirect technique. This time you're actually monitoring the brightness of a star as a function of time. And so if the planet is passing along the star, along our line of sight, a telescope pointed at the star from Earth, then you might see a dip in that stellar brightness. And so that tells you that a planet might be there. And so a bigger planet will block out more light, a smaller planet will block out less light. And so you're getting a handle then on the planet's size. And so together, those two properties give you a sense of the planet's density. So is it more like a rocky Earth or something more like a gas giant? And so these are the kind of, in vogue detection techniques that have really produced quite a few planets, a lot of the histogram spikes you see here on this plot. But I'm really excited also for the future techniques that I think will discover even more planets and tell us more things. Get this animation going too. So first, actually, both of these techniques will be employed by the Nancy Grace Roman Space Telescope, which is another telescope that's going to be launched in the mid to late 2020s. And so this will employ two techniques, microlensing, which actually utilizes Einstein's concept, or gravity, the bending of space-time. And so a lot of this goes over my head, quite frankly. Microlensing is very much an abstract technique for me. But what's really cool about it is it detects planets as it's free-floating planets out in the sky. And so it's essentially a magnifying glass to find planets. So if you're looking at a lens star, and there's a planet there, there's this additional magnification. So again, it's kind of brightness of the star. And so what's really cool about microlensing actually is that it's insensitive to the planet's size. So you could find something as small as the moon or something bigger than Jupiter. And so that really gives you a handle of, how common are different types of planets in the galaxy. But I'm particularly excited about direct imaging as a technique. So all of these techniques that I've discussed so far have been these indirect techniques, but ultimately we'd love to take a picture of the actual system. We'd love to take a picture of the planet and actually extract information directly from the planet itself. We've been clever about it so far, and I'll certainly talk about it, but ultimately direct imaging is where we want to go, particularly if we want to try and find Earth-sized planets around sun-like stars. But it's very challenging because when you're trying to image a star and a planet together, the star is so bright that you essentially have to figure out a way to block out the stellar light such that you can actually see the planet there. And so there are varying techniques from the Roman Space Telescope, as its shortened name, is going to be employing a coronagraph, which is one of the techniques that you can actually block out the stellar light to detect planets and to characterize planets. So anyway, these are just asides before we get to the nitty-gritty of James Webb, but just to give you a sense of the really, variety of techniques, and there are a lot more that I didn't, describe here. And so I'll just say, Kepler Space Telescope has been pretty fundamental in our understanding of, not only planets themselves, but how common certain types are. Kepler was launched back in the early 2009, I think was the date. It's, since been retired, but it really was really important for understanding, how common certain types of planets were in our galaxy. And one thing I'll continue to plug throughout my talk is here on the right, you might have seen these online. So there were exoplanet themed posters that were made for various missions for which exoplanets factored in heavily. And so this is one artist poster for Kepler. I'll show a couple of these throughout the talk, but these are publicly available. Please feel free to download them offline. They're really cool. They all have different styles. So I'll highlight a couple of those over the course of the talk. And so when it comes to exoplanets, what are the sort of big questions that people like me, other people like Aidan, what are people thinking about? And so in my case, my primary focus in terms of my own research is on the weather and climate of exotic worlds. And so I'll talk a bit more about what that entails, why it's important. But that's kind of my the thing that keeps me going. But ultimately, we exoplanet scientists are really excited about the potential for habitable planets. Is there life out there in the universe? And identifying these so-called biogenic gases, so things like water or carbon dioxide that we know on Earth is fundamental for life, that, our hope is that we can find those gases around planets that might be in favorable conditions for life. And so that's really our ongoing quest. Okay, so just to set the stage in terms of, the types of observations we can make before I get into some of the finer details of the certain observations. How can we actually, extract any sort of information about transiting extrasolar planets? I told you that, we're observing the star primarily to extract information about the planet itself. And so how do we do that? And so one fundamental thing that I'll establish here is that a lot of these planets are very close into their stars. So in the case of actually this population called hot Jupiter, some of which I'll be talking about today, these planets are Jupiter in size. So they used the transit technique to determine that. But they also found out that these planets were orbiting at 10 times closer than Mercury orbits our sun. So they're very, very close into their host stars. And so what that actually implies ultimately is that these planets are tidally locked or synchronously rotating. And so one side of the planet we assume faces the star, and one side of the planet faces away from the star. So it's a permanent day side and permanent night side. And so while that's completely different from some the way Earth orbits our sun, or Jupiter orbits our sun, it provides us with an opportunity to kind of take advantage of that geometry to then extract information about the planet. And so ultimately we're subtracting off the information that we get combined from the star and the planet, and so then we're left with stuff about the planet itself. And so I'll start at primary eclipse, which is what I was showing in the animation. So at primary eclipse, you're seeing the planet's night side rotating into view, right? So that's facing away from the star. And so if you subtract off all the stellar information, the stellar light that's transmitted through that annulus that is the planet's atmosphere gives you some information about things like the opacity. Essentially means that the composition. So and the composition is important because it tells you, depending on what molecules might be there, how the planet's being heated and cooled. So that's really important for understanding, things like climate. When the planet passes behind the star, here in red over the top left, that's called the secondary eclipse. And so there you're basically getting the planet disappears behind the star and then reappears again. And so you're getting information about the planet's day size. So that's what you're seeing visible during that time. And so depending on the wavelengths that you're observing this planet, and we'll talk a little bit about this too, at infrared wavelengths where you're seeing kind of emitted light, you might understand things about the planet's temperature, also the chemistry to some degree. But at visible wavelengths, you're actually seeing light that's actually reflected from the star off the planet's atmosphere. And so that tells you even more about the planet's climate. And then my favorite part is these phase curve variations. So if you can observe between primary eclipse and secondary eclipse for these long duration observations, you're getting what's called a phase curve. And so that actually tells you loads of information about how the structure of temperature, chemistry, and so forth varies as a function of longitude. Because as I said, you kind of know what portion of the planet you're seeing as a function of time. And so this was one of the most famously done, I'd say, for me. This was really the first major phase curve observation of the exoplanet, was for the hot Jupiter HD 189733b. And I rattled the name off. It reads like a phone number. Planets are designated based off of the stellar catalogs that were originally used to search for exoplanets. And so the letter B indicates that there's a planet there. Oh, let me restart this. And so yeah, basically this was one of the first hot Jupiters discovered and known to transit its host star. And so what the Spitzer Space Telescope did is to observe this planet as it orbited the star. So compute this full phase curve. And so what's really cool about that is you can actually take what's essentially the emitted light of the planet as a function of time or phase and make a map. So kind of how hot the planet is as a function of time. And so you can make what essentially is a temperature map of the planet. And so I think the next slide, yeah. And so this was from the press release you can see back in 2007. So what this map was constructed based off of this phase curve. And what you can see, this is just a simple projection of the map. But given all of the things I described, right, the permanent day side, the permanent night side, you might expect that the hottest region of the planet, I don't know if you can see my cursor here, is right at the center, 0,0, right? That's where, the stellar light is being deposited. That's where it shall remain, right? That's what you might expect. But in fact, what the observation showed is that there's actually an eastward shift of this hotspot. So it was eastward from what was perhaps expected. And so this was really, the slam dunk for arguing for weather taking place in these atmospheres. These winds are driving the hotspot eastward. And so this is where a lot of my work comes in. And so my research involves taking what are called general circulation models, or GCMs. You might also hear global climate models, of planets that, we use these planet models to predict weather on Earth, on solar system planets. And so all of the same fundamental physics applies. And so you can adapt those models for particular planets. In this case, I'm showing a simulation here about another hot Jupiter, WASP 43b. You can see this kind of similar hotspot. This is just a temperature map as a function of latitude and longitude. And so taking these 3D simulations, so you're doing these cuts as a function of latitude, longitude, and pressure, taking those and producing simulated observations that you can then compare to actual observations that are taken with facilities like the Hubble Space Telescope. And so this is what's shown here on the right is a phase curve shown kind of in the raw data sense. So you saw kind of a map version. This is actually the data. And so it's essentially plotting the same sort of information. The flux, is, as it's called, is a function of orbital phase. And so again, what sides of the planet are visible as a function of this phase. And so you can use your models to then try and say, okay, do we understand the physics of what's going on in this atmosphere? Is there something that's going, something that maybe we're missing? And so the different curves here are showing essentially different compositions. So one is more enhanced in metals, some of the molecules that are heavier than hydrogen and helium. it seems to indicate that this planet might be enhanced in some of those molecules. There also might be clouds that are forming on the night side, and that's what's causing this discrepancy between the black and the colored curves there. And so it's really important to have both the observations and these complex models to really try and bridge the gap in our understanding of these planets. So I probably covered a lot of this already, but I'll just briefly go through. And here I'm showing another really cool animation of another exoplanet I'll talk about in a couple slides. But, it's really, at first glance, you might think that using these full 3D models might be kind of overkill. These are faraway planets. We don't know too much about them. Why we're even, dedicating this time. But it's really important to, study the extremes. A lot of these planets, that I just described, right? This hot Jupiter is really at the extremes of what we knew that, planets could potentially be. And so, solar system planets in general are fairly, fairly calm in comparison, fairly low temperature, fairly cool. And so, extending our models that are established in physics beyond, the regimes that we could have imagined, high temperatures, high gravities, high rotation rates, all these things, ultimately helps to inform our overall understanding of atmospheric physics, how atmospheres move. We can obviously understand three-dimensional processes. These are 3D models. So, the temperature, how the planet heats and cools, the composition, the clouds, the chemistry, all of that can really tie into our understanding through these models. And there's a lot of balance between some simpler models. So a lot of times we use 1D simple models to try and understand, maybe certain specific things that we can model very intricately. And 3D models are kind of the converse to that. You can maybe model a lot of things, but maybe it's a different level of intricacy in terms of how detailed you can model the clouds, say. And so they're really a nice, I think, a useful balance between those two. And finally, we're in an age now where it's not just, I said in the earlier histogram plots, right, where it's, over 4,000 exoplanets that have been discovered. And so, we can really start to do these detailed models and then start to compare them planet to planet to see, what kinds of trends we can observe between certain types of planets. We can ultimately start to conduct these comparative studies. So like we compare, Earth, Venus, and Mars in our own solar system, we can start to do those same comparative studies for some of the larger planets that we've discovered, exoplanets we've discovered. Okay, so getting into the nitty-gritty here. So just to kind of set the stage, again over, how much exoplanet science has really evolved over the past, decades. And so, in the early days, right, when Hubble was launched, right, in 1990, the first exoplanets weren't even really discovered. That was always a, theoretical construct, but Hubble was not designed fundamentally to observe exoplanets. They didn't exist at that point. And so, when exoplanets were discovered in the, mid 1990s, the early 2000s, Spitzer was also a key player in that, I already mentioned. And so I think what's particularly incredible about those two facilities in particular is how much ingenuity and innovation went into what instruments are already out there. How can we utilize them for our purposes to understand exoplanets to the best of our ability? And so it was really a great example of making do. These are incredible telescopes, but just trying to think creatively about how to use these instruments, how to use these facilities to the best of our ability. But then, of course, over the next next few years, there started to emerge telescopes that might have discovered planets, characterized planets, but these were purpose-built for exoplanets. So once we kind of knew the types of things we should consider when we build instruments, those sorts of considerations then factored into missions like Corot, Kepler K2, TESS, which you might have heard about, that launched in 2018. And so it's really exciting now to see more and more telescopes emerge with instruments that are purpose-built for exoplanets and exoplanet characterization, and Webb is no different. And so with that, I'll launch into talking a bit about Webb. And I know it's not a ton of time, so certainly ask me a lot more questions than what I'll cover today. But as Aidan said, set to launch on December 18th, 2021. So these are incredible pictures of the telescope fully unfurled. So there was quite a lot of extensive testing for this 6.5 meter telescope in 18 segments that you can see here. So this is over at Northrop Grumman, which is actually not too far from where we are on the West Coast anyway. And so they were doing quite a lot of extensive testing to make sure that the solar sail here unfurled at the bottom that you can see, as well as the telescope itself, everything was working properly before you want to pack it up and ship it away and launch it into space and then have it do all of that stuff again. It's if you can, there are, I think, quite a few videos online showing the full process of Webb being launched and unfurled, and so it'll be quite a stressful few weeks, perhaps months, until that happens fully. But nevertheless, yeah, really incredible to see it in this way. And so so far I've already talked a bit about infrared light, in regards to Spitzer, but just to give you kind of further context here, I've plotted the electromagnetic spectrum, and so you might be familiar with that. You see the gamma and X-rays, your shorter wavelengths, the ultraviolet, and the visible is really where Hubble had its kind of bread and butter. It did a lot of that work, a little bit into the infrared. And then on the other side, I've already mentioned Spitzer, infrared, but very much in the longer wavelengths here. Here I'm showing numbers in the bottom in nanometers is the units. So, James Webb really kind of bridges that gap, I would say, between what Hubble understood about exoplanets and what Spitzer did. And so, we've kind of reached the state of the art in our understanding for those facilities. And so it's really exciting now to kind of essentially fill in those gaps in our understanding with James Webb. And so I know we've talked about infrared light already, but just to further illustrate kind of what are the things we're seeing. Here it's just two images of different animals in visible light. So here on the left are meerkats. Here on the right is a freshwater crocodile that's just climbed out of the water. And so this is what obviously they look like in visible light. We've seen these sorts of things before. But if you were to observe the same animals in infrared light, this is really kind of illustrating, why infrared is informative for our understanding of, animals and other things like we'll be observing with these instruments. In the case of meerkats, they're simply emitting their own, body heat. So that's what we're seeing. That's why they're glowing as they are. In the case of the freshwater crocodile that's just climbed out of the water, it's still actually cooling off. And so that's why it's actually not as kind of glowy in comparison to its surroundings. And so, this is the same sort of information that we're trying to get at with our infrared observations with James Webb. And so with James Webb, there's 4 instruments that are going to be aboard the telescope that cover these near infrared and mid infrared wavelengths here. And so again, here I'm highlighting the Webb exoplanet poster, which is actually my favorite of the bunch. Again, please download them, put them everywhere. And so let's see. So we've got these 3 in the near infrared, near spec, nearest, and near cam. So they're all shown in their acronyms defined here. And then the mid infrared instrument called MIRI. And so with these different wavelengths, we have access to quite a few different molecules. So I've talked a bit about already the chemistry of these atmospheres. And so here's just a schematic showing you a generic spectrum of an Earth in this case. And so, if a potentially habitable planet were to have things like carbon dioxide, the molecules that we have in Earth, carbon dioxide, oxygen, methane, et cetera, these are the sorts of signatures that we've been able to see with James Webb. And I'll note that, with Spitzer, we had maybe some access to those same wavelengths, but not the same spectral resolution. So to be able to actually see this particular signatures. In the case of Hubble didn't really had a limited access to some of these molecules, maybe, water in some cases, but there's a benefit to not only going to longer wavelengths, but also a bigger telescope. So collecting more light from these planets. Okay, and so I think, I'm not sure, how am I on time, Aiden?
You can keep going for,
okay.
as long as you want,
sure.
really. But
yeah, no, okay. No, I've only got, I haven't got a ton more slides yet. So yeah, just the last few slides are really just kind of closing out programs that I was very fortunate to have been awarded James Webb time. And so when people want to observe on a telescope, they typically submit a proposal, it's evaluated, and so some subset of those submitted proposals are selected. And so I was very fortunate to have a few selected, actually. And so this one I'll talk about in particular is, so I highlighted the title just because I enjoyed it, the proposal that I wrote, A Blast from the Past. a spectroscopic look at the flash heating of HG 80606b, another phone number planet. So this one I actually showed an animation for. I'm actually just going to skip ahead here. And so what's really interesting about this planet is it's a planet on an eccentric orbit. And so far I've kind of been talking about planets on circular orbits. And so this is a Jupiter-sized planet, but it's on a highly elliptical orbit. So it orbits its star every 111 Earth days, but its eccentricity is 0.93, which is actually, from on the very, very much extreme end. And so what's really cool about that is you can actually, if you observe the planet as it approaches its star, it's so-called periastron passage, that tells you something about how an atmosphere in general responds to extreme heating. And so, you essentially get a laboratory all in one. You can observe the planet when it's really cool, you can observe it when it's really hot. And so understanding, how chemistry, how clouds, how all of that kind of plays into that environment, or how it responds to that environment, is what this system is offering. And so that's basically our plan, is to observe the planet before it approaches its star and after it approaches its star, to understand things like how fast does it heat up, how fast does it cool off, what sort of chemistry might play into that factor, how is the planet rotating near that orbit, how is it tidally interacting between the planet and the star. So these are lots of things we can unpack with really this single set of observations. Another thing I'll just briefly highlight is a technique called eclipse mapping. And so I've described phase curves already, right? You're getting this full phase of the planet as it orbits its star, but you might imagine that a lot of it can be very time intensive, right? You're staring at a system for a very long amount of time so you can get all that information, just to understand, things like the temperature as a function of longitude. But this technique is, I'd say, very complementary and less time intensive, but for perhaps a similar amount of information. And so here, you're actually just taking, you're monitoring very closely the so-called ingress and egress of the secondary eclipse. So as the planet passes behind the star and in front of the star, you're seeing different chords of the atmosphere in that time. And so by mathematics, you can essentially compute a 2D map based off of that ingress and egress. That's what that cartoon is essentially showing you. So this combined map actually gives you a very detailed map of the planet day side. And what's particularly cool about that is it's showing you information as a function of latitude. So far I've only talked about longitude, but here you're getting latitudinal information as well. And so this is for HG 189. I've already mentioned this planet. And so previous observations seem to suggest this northward shift of the hotspot that I've been describing. But the analysis, the quality of the data was such that, there might be some uncertainty there still. And so, James Webb will be able to do the same sort of exercise, but with more wavelengths, therefore probing different regions of the atmosphere. So at different wavelengths, we're actually probing different, higher up in the atmosphere or deeper in the atmosphere. And so we can then compare to detailed simulations like this GCM here that I'm showing that I ran. So comparing our retrieved maps of the day side to maps that our models have produced. And so, yeah, these are, I think, my last two slides. So, but ultimately, what's also, exciting for me is the potential to search and detect biosignatures on an exoplanet. And so, for an Earth or maybe a Titan, you might see different signatures, right? On Earth, we'd expect, I'll play this one more time, things like methane, carbon dioxide, carbon monoxide, oxygen. But for a planet that might be habitable, but might look very different from our Earth, you might just see a bunch of methane. And so James Webb might be able to detect some of these signatures for certain types of planets. In particular, I'll go to the next slide. I think this is my last slide. You might have heard quite a bit about the TRAPPIST-1 system in the past. So this is a system of 7 roughly Earth-sized planets orbiting an M-dwarf star. So this is a star that's about half as cool as our sun. And so all of them are transiting. So that's what this crazy animation is shown. These planets were discovered from the ground with a ground-based telescope, but then followed up with Spitzer. So that's where all these observations come in. And so James Webb has a lot of dedicated time to actually, some of the first observations that it's going to make is of this system. And so people are really excited about the prospect of potentially detecting, biosignatures, these biogenic gases around planets that are in the habitable zone. So planets, I believe E and F, are in the kind of Goldilocks zone, you might say, of favorable temperatures from the star to potentially host life. So anyway, I don't have a conclusion slide here. But I'll just say, so ultimately, our hope is that we'll kind of circle back to this pale blue dot and try and find one of those out in the universe. And so, with James Webb and beyond. So with that, I'll take questions.
Okay, thanks so much, Tiffany, for this talk.
Yeah.
So I should have said this at the beginning, but if anybody has any questions, please feel free to post them in the chat. And there's already a couple.
Cool.
So one person asked, how many hours or nights of observation does it take to get the data that you use? And maybe more specifically for those 2 planets that you mentioned.
Sure. Yeah. No, it's a great question. And so for the planet, the HD 806 planet, the eccentric, the elliptical one, that's overall like 24 hours worth of observations. And so we're observing 11 hours before secondary or before periastron, before that close passage, and then another 11 hours after. In the case of the eclipse map observations, I think it's similar on the order. I can't remember off the top of my head, but it's like 10 to 20 hours, something of that size. But yeah, phase curves, in general can take quite a bit of time, just to make sure you're monitoring the full transit, the full secondary eclipse. It all depends on the orbit of the planet you're trying to observe. Yeah.
And they asked sort of follow up to that, which is like, how has the time to observe it changed with like JWST compared to if you wanted to do this with an older telescope? Would it have been possible, or?
Yeah. No, it's a great question. And actually, the eclipse map, I'll just go back just to show it. So this was a James Webb program, but I actually have an awarded Hubble program to do some similar eclipse mapping. And so it's been, cool to compare and contrast that. But basically, we're able to build. So with Hubble, we're using something like tens of eclipses basically to build a similar map of this resolution. But with James Webb, we're actually only using, I believe it's 8 eclipses. Sorry, 8 eclipses for Hubble and then 1 eclipse for James Webb. So that maybe gives you a sense of the kind of signal to noise. Thank you. Yeah, Aiden's nodding. So that just gives you a sense of like the signal to noise that is required with James Webb as opposed to Hubble. So, no knocking Hubble, but, it's definitely taking a lot more observations to kind of build the same essentially resolution of this map as compared to James Webb. So yeah, it's sort of more time efficient in kind of all those axes in signal to noise basically too. Yeah.
So another question that some people might be wondering is, how hard is it to get time like this on JWST?
Yeah, I mean, it's very challenging. So this was the first, open, so a general observer call. So there's a lot of claim time right up the front. So when, James Webb launches, there's guaranteed time observations, or GTO time. That's kind of all the people who, built the instruments have first dibs, which is totally fair. And so even they have their own process for, putting in proposals and getting them selected. And then there's early release science. So that's kind of the first, this is the first time they'll be launched into space, right? And so we need to do a lot of testing to understand, how the instruments are going to work in space. And so these early release programs are, a lot of like big collaborations to understand, how these instruments perform so that we can be more successful in programs like these. But ultimately, yeah, I mean, I don't remember the numbers off the top of my head, but it is fairly competitive. And so, you submit a bunch and you kind of hope, but it's, I think, a good sign that there was a lot of demand. Obviously, a lot of people are really excited about it. So, yeah.
Another person asked, can some gases have a range of explanations, like volcanism, outgassing from rocks, or even oxygen? So what they're asking, like, how definitive are various biosignatures?
Sure. No. Yeah. And that's a big challenge actually. Is the oxygen that we're potentially detecting, is that from an atmosphere? Is that from life? Is that just a random outgassing event from, I don't know, some, yeah, a fissure on the surface? Those are exactly the sorts of things that, detailed models like these will have to, rule out those scenarios. A good example of this, not for habitable planets per se, is but just illustrating kind of the complexity. I didn't talk about this planet, but it's called 55 Cancri E. There was a travel poster actually that's out about this planet if you want to learn more about it. But what's interesting about it is it's a rocky planet, but it's at those same distances that I was describing to its star. So it's like 0.1 AU. It's 10 times closer than Mercury's to our sun. So essentially, it's really hot, right? And so it's a lava planet in the broadest sense. And so, but what people haven't really have been trying to understand is whether or not the planet has an atmosphere. So is the surface, is it rocky, or is it all magma? Is the particular molecules that we're detecting from the atmosphere, is that outgassed from the surface? Is that actually in the atmosphere? Or is it by some other chemical process? Yeah, these are exactly the sorts of things that we'll need to essentially rule out certain simulation or certain situations or yeah, to really get at, is this planet habitable? So thank you for touching on that, because that's exactly what what challenges face us when we're like, okay, we found the next Earth 2.0. We want to be absolutely sure. Yeah.
One question that's kind of related to the biosignatures is,
Mm-hmm.
do we have a lot of targets that we can search at the moment? Do we have like a lot of good targets, or are we
Mm-hmm.
still do we still need to sort of find good targets to look for biosignatures with?
Yeah, no, that's a great question. And so, yeah, I'd say there are some good targets. So the test mission, the Transiting Exoplanet Survey Satellite, its whole goal is to look for transiting exoplanets similar to what Kepler did, but around brighter stars. And so what brighter means is that they're more favorable for follow-up observations with things like Hubble or James Webb. And so there have been quite a few small planets found through that program. So I imagine there will be quite a lot of effort in the future to try and search for biosignatures maybe on some of those planets with James Webb. But in the future, if we want to search for an Earth-sized planet around a sun-like star, so far, TRAPPIST was around this ultra-cool dwarf, with searching for an Earth-Sun system like our own is perhaps going to require a future telescope that will have the capability to do that. So the direct imaging capability on James Webb won't be able to accomplish that. And so, there might be some level of, depending on, what mission might be recommended in the future, there might be some element of searching for those systems first with those telescopes, and then, doing follow-up characterization. So yes, in the short term there are, but they might not be quite as, duplicate like Earth 2.0 in terms of the sense of orbiting sun-like stars. Yeah.
Right. Okay. Well, I don't see any more questions at the moment. So, and we only asked you for 30 minutes, but you've stayed with us for 45. So
No problem.
thank
Happy to
you
do
so
it.
much for talking to us about JWST and talking to us about your research. Yeah, it was very interesting, and I think everyone
Awesome.
really appreciated it.
Yeah.
So thank you very
Great. Well,
much,
thanks for,
Tiffany.
yeah. Yeah. Thanks very much, Aiden. And thanks for the great questions. Those are awesome. Yeah. Enjoy the rest of the show.
All right. Good night. All right. So for the rest of the planetarium show, as we usually do, I'm going to do a Stellarium show. Okay, Earth is life. I just saw that you have a question. You can still ask it, and I might be able to answer it. But anyways, so for the rest of the show, I'm going to be doing the virtual planetarium show. I'm going to be showing you the night sky tonight from Los Angeles. And to do that, I'm going to be using software called Stellarium. So I'm going to just go ahead and get that up at the moment. just bear with me for a minute. I'm going to disappear for a second, so don't be concerned. All right. So hopefully you can see me now and hear me. So before we move on, I'll answer your question. So you asked, will James Webb be able to see the moon landing sites in more detail? So the answer is probably not, and the reason is just because the moon landing sites are really, really, really small. I think to be able to see the moon landing sites, or be able to resolve the flag on the moon at least, you would need a telescope the size of the Earth to do that. And that's a physical limitation. It's not just a technology limitation, it's a physical limitation of basically all telescopes. Now you can still probably resolve the actual larger site with a telescope that's not quite that big, but it's still very difficult. So Webb probably won't be able to do too much better. It'll do a little better, but it's still very small. All right, so I've opened Stellarium now. So hopefully you can see me in the right corner. So I'm going to start by just sort of explaining what Stellarium is. So this is a virtual planetarium software. And what it's going to allow us to do is look at the night sky over Los Angeles as it is tonight, essentially right now. So we can move around the sky at will. We can change the time at will to see how the night sky will look without having to actually wait for the sky to change. So everything I show you, you'll be able to see tonight or tomorrow night or in the next few weeks in the sky in Los Angeles. And if you're at a latitude that's similar to Los Angeles, you'll also be able to see all these things. If you're at a latitude that's more than 20 degrees away from Los Angeles, the night sky will be different for you. So keep that in mind. So the landscape that I've put into Stellarium is Los Angeles, since we're based in Los Angeles, and this, for people who live here, this will help give you some reference point. So right now, our viewpoint is at is just below the Griffith Observatory. So we're on the Griffith Observatory mountain in Griffith Park, and directly to our south is the city. To our north is the observatory itself. To the west is Westwood and where UCLA is, and then east is out towards Pasadena. All right, so this is before sunset, and I just moved to before sunset to sort of orient you on the locations, and you can see the cardinal directions in red here at all times to keep you oriented. I'm going to go ahead and just instantly warp to the current time to show you the night sky right now. And keep in mind that in Los Angeles, we have pretty bad light pollution. So many of the stars that we're going to see here, you probably won't actually be able to see in Los Angeles. But a lot of them you will be able to. And if you go outside to a dark site, obviously there'll be lots more stuff to see. Let me see. Oh, and Earth is Life, you asked, how did I add the landscape? There is, if you have basically 360 images, spherical images, you can add them as landscapes. It's not completely easy, but it can be done. So, all right. So before we talk about any objects in the night sky, I just want to talk about the way the night moves. So just like the sun, all stars rise in the east and then set in the west. So if I were to fast forward through time from now, and we're looking east, we'd see all of the stars rising in the east. We see the moon rising. And then if we were to go back and look towards the west, we would see all of the stars setting. And then if we were to look towards the north, we would see that the entire night sky rotates around a single point, which is the north celestial pole. And by chance, there happens to be a star there in the northern hemisphere, which is the North Star Polaris. And that's what I've just clicked on here. So in LA, it's about 34 degrees above the horizon. And so you can see it's just above Griffith here. And again, if I now go backwards in time through the night, you'll still see the entire sky rotate around Polaris. There doesn't have to be a star at the pole. And if you go to the southern hemisphere, there's not really a bright star at the south celestial pole. So there's no south stars. So it's a pure coincidence that there is a North Star. A lot of people think that the North Star Polaris is a really bright star. It's actually not that bright. It's the 50th brightest star in the sky. So not anywhere close to the brightest star. So if you ever get lost in the woods and you're trying to go north or something, please don't follow the brightest star. That will definitely get you lost. The usual way to find the North Star is to use the constellation of Ursa Major, which is the Big Dipper. And unfortunately, in October, the Big Dipper isn't really visible very well at any point during the night. But you can kind of see it on the left here in the northwest, going behind the Big Dipper. And the two stars at the very end of the Dipper always point to the North Star. So that's how you can find the North Star relatively easily. And so Jason, there is no South Star. So there just doesn't, so there is a star that's a South Star, but it's just not very bright at all. In fact, it's much dimmer than Polaris. So you really can't see it very well with your naked eye. All right, so that's how the sky moves. And I'm going to turn these constellation lines off. And I want to go back to the south sky right now. And I did change the time, so I'm going to just change it back to what it is right now. And I want to talk about the brightest objects that we can see in the night sky right now, which are the planets. And so in the evening in October, we have 3 different planets that we can easily see. The brightest one is Venus, which you can see very prominently after sunset. And so it's almost setting right now at about 7:50. But if we were going back to when the sun set back around 6:30, you'd probably notice this really brightly. And, if you just notice it out of the corner of our eye, you probably just think it's a plane or something. But it is indeed Venus, and Venus is very bright. And if you were to actually zoom in on Venus, if you have a telescope, one cool thing about the planet Venus is that it actually has a phase to it. So only half of the disk of Venus is illuminated right now, and that's because Venus is interior to Earth. So because it's interior to Earth, we can always see basically some of the dark side of Venus. So Venus has a phase and it changes throughout the year, just like how the moon changes phase. And right now it's at about half phase. So that's the brightest planet of the night. And it does set, it's about to set right now. So at about, 7:50. So it sets at about 8 o'clock. We have 2 more planets, and I'm going to go back to the current time, 7:50. So we were earlier. Now I'm going back to the current time. And we have 2 more really bright stars, or sorry, planets, and that is Jupiter and Saturn. So if you go outside right now and you look directly south, you'll see Jupiter. Jupiter is very bright, so it'll be hard to miss. And then there's Saturn a little bit to the west of it. And Saturn is a little dimmer, so it's possible to mistake for a star, but if you know that it's near Jupiter, you'll be able to find it. And once again, with Stellarium, we can zoom in on these planets and check them out. So if you have a small pair of binoculars or a small telescope, you'll be able to see some of the details that I'll show you here. But if we zoom in on Jupiter first, just because it's brightest, you can see that it has moons. And if you look at Jupiter with, again, a pair of binoculars or a small telescope, you can actually see the moons of Jupiter, the 4 Galilean moons of Jupiter, which are the brightest moons through that telescope. You don't need a big telescope at all. Really, like any pair of binoculars will let you see these. And so we can see 3 of the moons right now. I think one of them is probably behind Jupiter, but we can see Europa, Callisto, and Ganymede. And Europa is an ice moon that is considered a possible location for life in our own solar system because it has oceans of surface water underneath. And actually, I think JWST, one of the things that it will probably look at in our own solar system is Europa, because you can see actually water spraying out from the surface of Europa, and JWST will be able to get analyze that really well. Yes, it is rotating through the sky. So the night sky is moving, and you can't really notice until you zoom in very closely. Okay, so that was Jupiter. And now we'll go over to Saturn. And Saturn, it's a little harder to see the moons with, but of course Saturn has very prominent rings. And again, it's one of the most amazing things to see in the night sky. If you can get a pair of binoculars, and if you have a pair of binoculars, you probably have to set them on a tripod to be able to see this. But you can pretty easily see the rings of Saturn, and so you can convince yourself that Saturn really is a real object. It does have these rings. Sometimes it's hard to believe the first time you see it. You think somebody put like a picture over the telescope or something. But Saturn is a great object to look at. And you can sometimes see its largest moon, Titan, as well. And Titan is actually the only moon in our solar system that has a thick atmosphere like Earth. So a thick nitrogen atmosphere. So it actually has a very thick nitrogen atmosphere, albeit it's much, much colder than Earth. And it has seas of liquid natural gases like methane on its surface. All right. Let's zoom out from Saturn and Jupiter. And I want to show you that, so if you look at Jupiter, Saturn, and Venus, it turns out that they all land on an imaginary line in the night sky called the ecliptics. And so I'm going to turn on this line, if I can. There's markings. All right, so I'll turn on the ecliptic. And what the ecliptic is it's basically the plane of our solar system as seen in space. So all of the planets in our solar system lie on a roughly flat disk, and that's why they all sort of appear along this line in space. So you will only find planets basically near this line. And so you'll notice that this line always goes, it's always in the south if you're in the northern hemisphere. So if you're in the northern hemisphere, you will never see a planet if you look north. They'll always be in the south for this reason. The other object that lies along the ecliptic is the sun. So I just rotated back into the middle of today. You notice that the sun is on the ecliptic. And if you know the zodiac constellations, The zodiac constellations are constellations that lie along the ecliptic. And the constellation of the month is whatever constellation the sun is currently in. So that's how the zodiac constellations came to be. All right. So I'll go back to nighttime now, and we'll turn off the ecliptic and move on. And if there's anything anything specific anyone wants to see, I'm happy to take requests if they're doable. All right, I'm going to turn off the ecliptic now. All right, so those are the three bright planets that you can see tonight. Mars is not currently visible, and I think Mercury is maybe barely visible in the morning. Now I want to look at the constellations that you can see tonight. I'm actually going to turn off any light pollution at all, just so you can really see the night sky well. And I know it doesn't come across quite as well on virtually, but nevertheless. The first constellation that I want to talk about is Sagittarius. So if you look to the southwest tonight, right now, you'll see the Milky Way. And okay, if you're in Los Angeles, you won't see the Milky Way because, again, there's too much light pollution in Los Angeles to see the Milky Way. But if you can get out of Los Angeles to a dark site and you look to the southwest, you'll see a band of light across the sky. That's the Milky Way. And one of the constellations that lies along the Milky Way is the constellation Sagittarius. This is a constellation that's really hard to figure out what it actually is supposed to look like. So usually we use an asterism to find Sagittarius, which is the teapot. So the constellation Sagittarius looks like a little teapot with a handle back here, the top here, and then a spout here. So what's neat about this constellation is that it's very near to the location of the galactic center as we're viewing the Milky Way from the Earth. So it turns out the center of our galaxy is just off to the right of Sagittarius. So, and that is where there is a supermassive black hole, and it actually took a long time to discover that this was the exact center of our galaxy, because there's tons and tons of dust obscuring the galactic center. And so to be able to find the galactic center, you have to use infrared light, which, guess what? James Webb Space Telescope is going to be an infrared telescope. So James Webb will be able to provide great images of the galactic center, and I think there'll be some research with it related to the supermassive black hole there. But anyways, next time you go outside, if you can spot Sagittarius, then you can tell people that the center of the galaxy is just near there. Sagittarius is also great because there's tons of deep sky objects around it that are good to see if you have a telescope. One really great one is called Messier 22. Let me find it real quick here, which is a globular cluster. So I'm going to zoom in here. So this is M22. It's a globular cluster right above Sagittarius. And this is a collection of thousands or tens of thousands, maybe even hundreds of thousands of stars that are extremely old. So these were some of the first stars that were probably born in our galaxy. And you can see them here. So that's a great object, again, with a telescope. And that's just actually one of 7 globular clusters that you can see near Sagittarius. And the reason there's so many objects near Sagittarius is, again, because we're looking in the plane of our galaxy. And so there's just a lot more stuff in the plane of our galaxy. If we were to look, for example, in some other direction, not inside the galaxy, there's a lot less objects there just because we're not looking in our galaxy. All right, so that's Sagittarius, and it's in the southwest tonight. It does set fairly early, so you want to check that out early in the evening. All right, next constellations I'm going to go to are almost directly above us right now. And rather than talking about one constellation, I'm actually going to talk about 3 at once that form what's called the Summer Triangle. So if I zoom out now, so again, south is down here, and you'll see there's 3 really bright stars, Altair, Vega, and Deneb, that form what's called the Summer Triangle. So this isn't a constellation, it's an asterism, which is a just pattern of stars that are easy to see. And these 3 stars form 3 different constellations. If I turn on constellations rather than asterisms, Vega is the brightest star in the constellation Lyra the Lyre. Deneb is the brightest star in the constellation Cygnus the Swan, and Altair is the brightest star in the constellation Aquila the Eagle. And I can turn on the art for these constellations so you can see them. Something interesting about the Summer Triangle, and more specifically the constellation Cygnus, Tiffany was talking about the Kepler Space Telescope for a while. And when the Kepler Space Telescope first launched and it was looking for exoplanets, it just stared at one part of the sky for 3 years. And Cygnus is actually that area of the sky. So Kepler was basically staring at this part of the sky for 3 years. And for that reason, most of the known exoplanets that we know about are actually in this region of the sky. And you won't be able to see any of them, but again, it's kind of a cool fact that that's where lots of exoplanets are in the sky. All right. I'm going to move on now to a constellation that is in the northeast, and that is the constellation of Cassiopeia, which forms a really prominent W. And what's interesting here is not so much the constellation itself, but again, you can use this constellation to find one of the most interesting objects to look at in the night sky, which is the Andromeda Galaxy. So it's kind of hard to navigate from Cassiopeia to the Andromeda Galaxy exactly, but it's basic right now. If you look at Cassiopeia, it's basically, a few degrees east of the constellation. And the Andromeda Galaxy is the largest galaxy in our night sky, and it's also the closest galaxy to our own Milky Way galaxy. So if you actually look at the Milky Way, which is right here, and compare it to the moon, which is rising down here, you might notice that the Andromeda Galaxy is actually larger in the night sky than the full moon is. And it's actually significantly larger than the full moon. So you don't realize this because even though this galaxy is really big in the night sky, it's really, really dim. And again, this is something that you're not going to be able to see in Los Angeles because of light pollution. But if you can get out into a dark space, you can actually see the Andromeda Galaxy with your naked eye. And you won't be able to see any detail in the galaxy, but you will be able to sort of see a smudge of light where it is. And that's the farthest thing that you can see with the naked eye. It's 2.5 million light years away. So the light takes 2.5 million light years to travel to your eye. So it's been on that, if you can see it, then it's been on that long journey before it gets to you. And Dan, you asked what's my favorite thing to see in the night sky. I think the Andromeda Galaxy probably is one of those, as long as you can get to a dark place. If not, it's tough to see, but it's definitely one of the craziest things to see. All right. And you'll notice, so it is 2.5 million light years from us. So yeah, quite a long way. And the Andromeda Galaxy is actually getting closer to us. At the moment, it's actually on a collision course with the Milky Way galaxy. It will be a very long time before it collides with our galaxy, about 5 billion years or so. And you might think that that'll be a terribly destructive event, and it will be for the galactic structure. But for individual solar systems, it won't make too much of a difference. And the reason for that is that the distance between stars is so great that when two galaxies collide, the stars mostly just pass through each other. So if our solar system is still here in 5 billion years, then it will probably be completely undisturbed by that collision. And you will see the Andromeda Galaxy continue to get larger and larger in the night sky. So we also have the moon rising tonight, which you've probably been able to see this whole time. Tonight we actually have a full moon or almost full moon. So you definitely won't miss that if you go outside. That's actually not a very good thing for observing, for amateur observing in astronomy. The full moon is itself a sort of source of light pollution. So it makes it harder to see deep sky objects like galaxies. The full moon will make it hard to see the Andromeda Galaxy. A full moon is also not very good for observing the moon, just because it's so bright. Actually, the ideal time to look at the moon is when it's at about a quarter moon. And that's because when it's like that, you get really nice shadows across the moon, and those shadows give you a nice sense of depth perception on the craters of the moon. Whereas when it's at a full moon, it's sort of bright and flat. So it's not great to observe the moon when it's full, despite what you might think. All right, and I'm just going to show you one more thing tonight before we end. Already gone well over an hour. But if you stay up a little later tonight until 10 or even 11, you're going to see a constellation rise in the east called Taurus, the Bull. Taurus has a distinct Y shape, which you can see here. That's another asterism. If I change from constellations to asterisms, it has this sort of V or Y shape. And I can show you the constellation art as well. So there's Taurus the Bull. And again, this constellation, and you'll notice this is a trend. This constellation is interesting because of what's right nearby, which is the Pleiades star cluster. And actually, this is quite close to the full moon as well tonight. And so the Pleiades star cluster is here. So it's just above Taurus and below and to the right of the moon to the east. And this is a cluster of hundreds of stars, but there's 7 really bright stars in it. And this is one of the best clusters to see in the night sky. Again, you can actually see this cluster with the naked eye. So it's fairly easy to find. And there's 7 really bright stars, so sometimes it's called the 7 sisters. In Japanese, this cluster is also called Subaru, and the Subaru car company, their logo is stars, and it's meant to represent these stars. There are, in reality, hundreds of other stars here, and you can sort of see them if you have a telescope or binoculars as well. And this is going to be a bunch of young stars, and our own solar system would have formed in a cluster like this, but we don't realize it because our solar system's pretty old already. Our solar system's 5 billion years old, and so our sun has basically broken away from the cluster that it was born in, whereas this cluster, I think, is only about 200 or so million years old, which probably sounds really old, but in astronomical terms, that's quite young for a star cluster. So, all right. And with that, I'm going to wrap up our presentation for the evening. I see one more question. Are there examples of galaxies colliding today that you can see with your telescope? Yes, I know that there are. I'm not sure if I have a great example off the top of my head. Actually, I do know one example, although it's not going to be very well visible in this season. Actually, if I look north again and I bring up the Big Dipper, I'll rotate back. Okay, so here's the Big Dipper, here's the handle, and here's the scoop. There's a galaxy sort of off the handle here, and we'll see if I can find it. Okay, yes, here it is. Let's see. This is the Whirlpool Galaxy, or M51, and there's actually two galaxies colliding here. So there's one really big prominent galaxy, and then there's one off to the side here that's colliding. And that's actually why this galaxy has a very prominent spiral pattern to it. That's actually why the collision is causing this spiral pattern. I will say this is a pretty difficult target for if you're just getting into astronomy. So you probably need to get a little bit of observing experience to see this, which you may have, but just a heads up. And yes, so you asked why are there so many stars in the Subaru cluster? It is actually typical that all stars form in large clusters like that. And the reason is that stars form in basically gigantic dust and gas clouds in space. And these clouds can be hundreds of light years across. And when they collapse, they tend to sort of fragment and form tons of stars all at once, rather than just forming one star at a time. And for that reason, it's also quite common for stars to form in doubles or triples because of that. So there's actually about a 50% chance that a star forms in a double or a triple system. So those are extremely, extremely common. Even though you wouldn't think so, because we live in a solar system that only has one star. And thank God, because if we had two stars, that would probably not be too good for life on Earth. But all right, I'm going to go ahead and call it there for the evening. So thanks everyone for tuning in. I hope you enjoyed the special presentation by Tiffany, and then hopefully the night sky presentation as well. And just a reminder that we do these planetarium shows weekly. So there'll be another one next Wednesday and every Wednesday. At the moment, they're being done virtually, but we do have an in-person planetarium that we are hoping to open up in the near future. So stay tuned for that. And you can find all our events either on Facebook, or you can go to our website by just searching UCLA Planetarium. So you can stay up to date with us there. But otherwise, yeah, thank you so much for tuning in. I hope everyone's well, and good night.